So a few videos back we were talking about the different types of our power supplies or our voltage regulators, and the first type that we had looked at was our linear voltage regulator, or we can also call these linear power supplies. And then the second type, which we're going to be getting to today, is our switching power supplies. So first let's highlight again why we want something to improve upon our linear power supplies. So compared to our switching power supplies, these are going to have poor efficiency. And so the reason for that is because any of the energy that is not sent to the output, so for instance, if we're stepping down our voltage with our voltage regulator, any of that voltage that's not getting sent to the output is being dissipated as power in our series pass devices. So power is dissipated in the series pass devices. And so for the example we saw with our discrete circuit, that would be our transistor, our BJT that we had, and as well as that resistor that we used to sort of adjust that feedback loop. So we want to improve upon this efficiency, and so we said we can do that with our switching power supplies. And so we're going to take a closer look at some waveforms and see exactly how that comes about. But in general, we can say that with our switching power supplies, we're either on or off completely most of the time. So most of the time, on or off. And then we're just briefly in these transition regions. And so what we're going to see is in these transition regions is where we're absorbing or spending most of our power. So if we can limit that, we're not using as much power. So again, we're going to come back and we're going to even see for different types of circuits. In some cases, we might want to adjust our switching time. In some cases, we might want to adjust other things in order to keep this as efficient as possible. So this does have active components as well, like we're going to see when we look at some specific examples a little later on. And so what that means is that we're going to have nonlinear functionality, which means that not only can we step down now, but we can also step up. So we can step up our voltages as well. And so what we're going to do first here is we're going to look at sort of a general switching plots for voltage, current, and power over time. And then after we sort of go through this basic idea of our switching power supplies, we're going to come back and we're going to look at specific circuits, and we're going to talk about what those waveforms look like. So one other thing I want to mention about these switching power supplies is typically these are going to have a lot higher power density, and we're not going to need large heat sinks like we would for comparable powers with our linear power supplies. So again, better efficiency, less issues with overheating because we're not expending as much power. So let's look at our power consumption and switching plot down here. So this is going to show our power consumption and switching. And so we're going to make a few assumptions here, and I'll enumerate them after we've done our plot. But you'll notice I have three empty plots at the moment. We have on the top our voltage, in the middle our current, and on the bottom our power, all as a function of time. And so I've tried to align these plots in time so that you can see these dashed lines represent the same time in all three plots. So let's say we are considering a switching power supply. And so what that's going to look like, let's change to a different color here. So let's say initially we're at a maximum voltage, and that corresponds to our switch being open. And one of our sort of assumptions here is that we're going to assume that this is at zero current if our switch is open. So we're saying that we're not having any power consumption when it's open. So of course we know in general P equals IV. So if we multiply these two plots, we see 0 times V max is just going to be 0. Okay, so this is for our switch open. So now let's say our switch is closing, and let's sort of we're not going to assume that it happens instantaneously, but let's say there's some transition time going from switch open to switch closed. And so what that's going to be is we're going to say that our voltage is starting at V max and it's ending at V min. So let's sort of put a dashed line to show we're coming down here to Vmin. And so our second assumption is going to be that our voltage and our current in these regions is changing linearly. So I'm just going to put a nice straight line in here like this. And so our current, so our voltage is decreasing, so our conservation of energy. If our voltage is decreasing, we're going to be increasing our current here up to some current I max. And again, hopefully this will all make more sense once we see actual circuits and we can see why our currents and voltages are changing like this. But for now, if it's not intuitive, just kind of take my word for it, and we'll come back and we'll see more clearly why this is the case in later videos. Okay, so this transition, we're going to say this is our T switching. So this is the time that we're switching. And we're also turning the device on because we're going from an open switch to a closed switch. So I'm going to further denote this with parentheses on. So time of our switching, turning on. Okay, so then let's say we're on for some time between our next dashed line, so everything's essentially going to stay constant. And so before that, let me come back here and do our power. So if we're taking the product of our two powers, essentially what that's going to look like is we're going to have a almost parabolic shape, which is going to be peaking at some P max. So to align that with my plot, I'm going to put a little dot there, and we're going to have something that looks like that. Okay, so now we're going to say we're just going to be staying on. So our switch is just staying closed, so I'm going to call this T on, and everything's essentially staying constant. We have our voltage staying at Vmin, we have our current staying at I max, and because our voltage and current are constant, our power is going to be constant at some value as well. And so that value is in most practical cases for switching power supply is going to be lower than our P max. If it's higher than our P max, then we've kind of defeated the purpose of our switching power supply. Okay, so then let's say after it's been on for some time, we want to switch it off. And so keep in mind, we'll come back and look at this later, but we're not manually throwing a switch. This is something where the switching is happening very quickly and in prescribed intervals based on how we want to change our voltage. Okay, so let's say this is going to be our switching time again, but now it is our switching time to turn off. And this might or might not be the same time as our switching time to turn on. And so in this case, again, we're going to be transitioning from Vmin to Vmax. So now we're going back up to sort of that open circuit case of Vmax. And for our current, we're going from our closed circuit to our open circuit case, which was I max to 0 current. So we're coming down here like this. And again, down here, we get another little parabola shape, which is going up to P max and coming down here to 0. These two parabolas here should look pretty similar. Any difference is just from my inability to draw well, essentially. But again, if our TS and our I should correct that. If our TS on and our TS off are different time scales, then of course we might have one more stretched than the other, but they should roughly be around the same P max. Okay, so then let's say we have our switch open for some amount of time, so our device is off. So we can call this time T off. And so during T off, our voltage is just staying at a maximum value. Our current is just staying at 0. P equals VI, so if our current is 0, our power is also just staying at 0. So then let's say the whole process starts repeating again. So our voltage begins decreasing, our current begins increasing, and our power begins increasing as well. So we just have this sort of periodic repetition of this structure. And so essentially where you can kind of see where we're going with this is by adjusting our duty cycles and the configuration of our active components in the circuit, we can adjust the relationship between our input and our output voltages. Okay, so let's just go ahead and annotate on here sort of our assumptions. So let me put that in red. So let's over here write assumptions. And so our first assumption, and I've mentioned all of these sort of in passing, I believe, is we have a linear change during switching. So linear change during switching. And so that, of course, applies in this region where we have TS on and TS off for our voltage and current. So, for instance, here and here for our voltage, and here for our current. Okay. Our second assumption is that we have zero current when our device is off. So zero current when our device is off. And so in this plot, of course, that's talking about this condition, which ultimately leads to having zero power for those time intervals as well. And then the third assumption is that the device is maintaining our Vmin and Imax when on. So let's just come in here and say our device maintains Vmin and Imax when on. And so, of course, depending on load conditions, this might not necessarily be true, but we're going to simplify and assume it is for our preliminary analysis. So what we're going to do in our next video is we're going to come back and take a closer look at these plots here, and we're going to see if we can determine the energy in a switching cycle. And then from there, after we've looked at our general sort of configuration of these switching power supplies, we're going to go on to look at specific circuit topologies for different switching power supplies, which can achieve different types of outcomes.